Hello everyone, my name is Yuchen and I'm currently a first year grad student at Brown University. And today I want to talk a bit about extended persistence and in particular, I want to focus on how it relates to persistent homology. So let's start with the basic definitions. Let us consider a function f from a simplicial complex k to r, and then for every real number A, it is natural to consider two sets, namely the sublevel set and also the superlevel set. This gives rise to two sequences of spaces ordered by inclusion, and the persistent homology module is then the sequence you obtain by applying the homology function to this sequence of sublevel sets. If we further include the data from superlevel sets, we can extend this persistent homology module by including a sequence of relative homology groups going down. And here we're going to consider all the homology groups with coefficient in some field F. So we actually have sequences of vector spaces. These two concepts can actually be phrased under the same framework. And to make this more precise, I'm going to make the following definition of persistence modules, where we have a family V alpha of F vector spaces indexed over some totally ordered set. And we also have family of transition maps phi alpha beta from V alpha to V beta whenever alpha is less than or equal to beta. And this transition map should satisfy the identity property and also respect composition of maps. Then Gabriel's theorem tells us that if V alpha is finite dimensional for each alpha in theta, then this persistence module V is actually isomorphic to a direct sum of interval modules, IBD. So what this means is all the data of V are actually contained in these BD parameters, which we'll call birth and death. And here is a illustration that I really like. So as we see here, lambda is an element that first appeared in the vector space V alpha, and it persists until it eventually gets absorbed in the image of some vector space V alpha prime for some alpha prime less than alpha at the time beta. So we can say this lambda element is born at time alpha and dies at time beta. And what that means is this persistence module will actually have a summand of interval module over the interval alpha beta. Equipped with definition, we can then see that persistent homology modules and extended persistent are both instances of persistence modules over two different totally ordered sets. So for example, the persistence module can be considered as taken over the ambient set, the extended reals with the normal ordering. And for extended persistence, we can actually consider two copies of R. One copy for the chain going upwards, through the ordinary homology, so we're decorated with ord, and another copy for the relative homology chain going downwards, and we'll call it rel. And the total ordering is defined so that we have a normal ordering for the first copy of R, and we will reverse the ordering for the relative group going down. And whenever you're comparing some value in the first copy of R and the second copy of R, T-rel will always be greater than some S ord for any pair of S and T in R. And with the interval decomposition, we can further categorize them based on where the birth and death parameter lives. If both of them live in the ordinary group, then we'll put them in the ord class. Similar for the rel class, and the essential class will contain interval modules with birth time in the ordinary group and death time in the relative group. So far, we have been quite abstract, and we're going to actually move on to some more concrete examples by considering 2D images, or more generally, manifolds with boundary. So in this motivating example, we're going to actually consider a height filtration with the direction taken to be pointing rightwards. And if you consider this abstract snail shape image, we can easily compute the persistent homology. And in this particular case, the superlevel sets is actually correspond to the sublevel set of the flipped image illustrated here. And we can use this nice relation between relative homology and reduced homology of the quotient space to compute the extended persistent homology. So there are two observations that I want to highlight here. First of all, extended persistent homology give you a lot more information about the space. In particular, there is no infinity involved in any of the burst depth parameters. And in fact, we can define a Vassa's time distance where the distance between any two extended persistence modules is finite. And this will be beneficial for application purposes. And the second thing to notice here is all the values that are picked out by the extended persistent homology are actually achieved on the boundary of this manifold. And if we examine further, the burst time, for example, A2 here in the ordinary class is taken at the point where you will enter the manifold if you go rightwards, and the burst time B3 in the relative class is taken at the point here where you will leave the manifold if you go rightwards, or you will enter the flipped manifold equivalently. This observation is crucial and will actually make it more precise with the help of Moore theory. So Moore's lemma tells us that a smooth N manifold without boundary, and for a smooth function f, a point P is a critical point of f if locally it looks like a paraboloid. And we can extend this idea and define the boundary critical points where locally around the point P, it will look something like this form, where the eta is what we'll call the sign of the critical point, and it can take values plus or minus 1, depending on whether locally the values around P will be greater or less than the value taken by P, namely f of P. So here are two examples. For example, if you look at the point P here, you can see this is where you will enter the manifold if you're going rightwards. And this will be a plus critical point because locally all the points here will have a greater value compared to the value P taken under the height function. And similarly, the point Q here will be a minus critical point because locally all the point around it will take a smaller value. This will allow us to index our critical points, where the critical points on the boundary will get an extra sign. And in fact, there is a nice correspondence between the critical point and the burst and depth value of the extended persistent homology. In particular, the plus critical points can only be the burst or depth time for ordinary class, and the minus critical point can only be the burst and depth time for relative class. And for the height filtration over a compact N manifold with boundary, the story gets even better. In fact, we can completely characterize the extended persistent homology of the manifold as a submodule of that for its boundary. And this will make the computation very easy and allow us to do shape analysis where TDA shines. I'm not going to actually go into the detail of these theorem or the proof of them, and you can find the details in this 2022 paper by Catherine Turner, Vanessa Robbins, and James Morgan. Instead, I'm going to revisit the example that we saw earlier with the snails. So let's now look at the boundary of the snail and pick out the critical points. And note that all of these critical points will actually show up in the persistent homology of the boundary. And I color-coded the critical values based on whether it corresponds to a plus or a minus critical points. From there, we can translate this information into the extended persistent homology of the whole snail. We will keep, for example, the pairs of plus critical points, for example, A2, A3 here, and send them into the ordinary class of the same dimension. And for the pairs of minus critical point B2, B3 here, we will actually flip them and send them into the relative class of one dimension up. For all the critical values that get paired with infinity, they will be matched to essential classes, where the dimension will depend on whether the point is on the interior or exterior boundary, and the declaration, the odd or rail, will depend on the size of the value it takes in R. So in this case, A1 and B4 both lie on the exterior boundary of the snail, so the outer boundary of the snail. So this will be sent to the zero-dimensional essential class. And because A1 takes a smaller value, the ordering will actually be preserved here. On the other hand, B1 and A4 are on the interior boundary of the snail. So what we'll do is we will flip the ordering, and this will get mapped to the n-1 dimension essential class, which in this case is just one dimension essential class. So this is pretty much the story for eye filtration. And in some cases, it might be even more natural to consider a radial filtration. For example, some biometric data has a natural choice of center, and you might want to consider distance of points to this chosen center. It turns out that there is again a nice matchup between the persistent homology of the boundary and the extended persistent homology of the manifold with boundary, with a caveat that this will depend on where the center is. For example, it does make a difference whether the center is inside or outside of the manifold. Nevertheless, I'm again not gonna go into the detail of this, but leave you with this example to play with. And in fact, I did a master's thesis project on this, where some of these cases were considered, and you can check out some of the details here. But that's it from me for now, and thank you so much for your attention.